In this demo, we're going to now learn how to use the three-dimensional objective mapping routine. So I'm logged in into the Axios, and I'm going to go in ROMs mapping directory. And again, I'm going to open main 3D mapping.m, which is the list of our tutorials. And we're going to be working with tutorial number 4, which is the 3D objective mapping. So let's go to that tutorial. Okay, very well. So this tutorial actually is going to provide an example of how to map a three-dimensional volume from an existing grid. For example, in this case, from a run of the North Pacific model, which is a grid called NP6. So I'm going to take a field, three-dimensional field or three-dimensional volume from this grid, and map it into the three-dimensional volume of this other grid, which is the Northeast Pacific grid that we've been working so far. So the first step then is to load, the grid, a field from this North Pacific run. And so here I define a GRD-IN, which is the grid structure array associated with the input or source grid, if you like. I then have a CTL here that I can define based on one of the outputs file of the model. I'm going to load the temperature field in this case. I'm going to load the free surface field also. I'm going to compute the depth of the sigma layers for this particular grid because I need that. And I'm going to provide also the free surface so that this depth is more accurate. And then I'm going to also build a three-dimensional mask associated with the mask at the row points of this grid. So I'm going to take all this stuff here and I'm going to go and execute it in my MATLAB window. Unfortunately, the network is a little bit slow right now. Okay, cancel. Okay, so I'm in my MATLAB window here. Gonna fire up MATLAB. And I'm going to paste all this stuff here. So just to check whether this is working fine, I'm going to plot, for example, the temperature that I just loaded, say the free surface, and so this is my North Pacific grid. Okay, so it's a nice eddy resolving grid that I've ran some time ago, and so this is where we are, and we want to interpolate this to the following grid, RNT. Let's load the NEPD grid load dash NEPD, and let's put the contours of this grid here so we can see the location of the NEPD grid. This is guarantee underscore grid box is this routine that allows us to do that. Oops, sorry. First I have to produce this grid here. Okay, then I have to type hold on, and then I can plot the grid. And it's box M because this uses the RNTP LCM. So you could see here that this blue array is where the destination grid is, and this other one is the source grid. So we're going to map now this three-dimensional temperature from here into here. And of course, inside here, the overlapping region, the two grids are different. They don't coincide in the horizontal, neither they coincide in the vertical. Okay, so that's the problem that we want to do. So what are we going to do next? Well, we're going to load the NEPD grid, which I already did, its depth of the sigma coordinates in grd.zr, and also a three-dimensional masking associated with the NEPD grid. Okay, so I'm going to do this in MATLAB. Okay, so that's doing it. Okay, so now that we're going to do the three-dimensional objective map, as we did for the 2D mapping, we're going to create the PMAP, which is this map of that tells us for each point in the destination grid, it tells us what are the closest neighboring point in the source grid. And so in this case, what we're going to do is we're going to give the longitudes and the latitudes of the source grid. In this case, the entire North Pacific. We're going to give it the mask. and then we're going to give the the destination grid longitude and latitudes, and then 10 is the number of selecting neighboring points that they're going to use. Now, when I run this PMap, as you remember, even in the 2D mapping, it takes a little bit of time. In this particular case, if I ran this, it's going to take about, probably 3 minutes, 3 or 4 minutes. So, in the interest of time, I have ran this already, and I've saved the PMap in this array here. So I'm just going to load this PMap thing directly from this stored MATLAB file. So I'm going to go here, and I'm going to load it. Okay, so now I have my PMap array. Okay, so that's very nice. And so then the last thing, the step that I need to do is to just do the three-dimensional objective mapping. And here's the call for the 3D objective mapping. This is the function call. You can always type help of this routine here, and then you're going to have information about how to call. But in general, it's very similar to the 2D objective mapping in that it wants a longitude and latitude, and these are 2D arrays. And then it wants a three-dimensional depth of in this case, of the sigma coordinates of the North Pacific grid, which is the source grid. Then it wants the field, the three-dimensional field. And then it wants the output longitudes and latitudes, which can be 2D arrays of the destination grid. The depth of the sigma grid of the sigma layers for the destination grid. And then it wants A and B, which are the decorrelation length scales in space. And then the PMap, which is the mapping of the neighboring points. So it's a very similar call. So we can go here, and we're going to say that the decorrelation length scales A and B are both in longitude and latitude about 3 degrees. And then we're going to just execute this entire statement. Here, note that these 3 dots here just represent a line continuation in MATLAB, meaning that this would be one belong line, but because it doesn't fit, I'm just putting the remaining part of the line below here. So let's go in MATLAB, and let's execute this statement. And you can see that it should be pretty quick, in fact. So we did this 3-dimensional volume. Now, keep in mind that if we look at the size of this stuff here, this is 481 by 261 by 30 points. This is a huge amount of data. And also this destination grid is pretty big too. So this is pretty effective in mapping this 3-dimensional volume. The last thing that I'm going to do is I'm going to take this temperature array that just came out, and I'm going to mask with zeros all the points that are in land for my destination grid, which is represented by this mask 3D. In fact, you see it here that we had done a 3-dimensional masking for this NEPD grid. So I'm just going to do that, and go to MATLAB and F12. So we can plot this just for fun. We can plot, for example, the surface value of temp, this new array that we just interpolated, and this should look very similar to the values. I'm sorry. What did I? It says missing variable or function. Let's see. Oh yeah, sorry. There was a comma here. Okay. So you can see this is now is the surface temperature in the quadrant, and we can check whether this is any true by we can clean this, for example, and we can do subplot say 1. We can plot instead of this, we can plot the temp in, which was the original the temperature of the source grid. Okay, hold on. Then we can take the axis of that, and we can plot in the one below. We can plot the one that we just interpolated, and we can put it on the same axis. Okay, and you can see already by eye that these look very similar, and they're very close together. Now the next step is, however, once we do this mapping of this 3D volume, which is a typical thing you would do when you do nesting, for example, you go from, say, this bigger grid or a spatially more extent grid to more high resolution, regional grid. So this is actually what you do in the nesting, and the point is that here now the objective mapping routine does give us an answer, but how good is this answer? And so in the next tutorial, we're going to assess, ways of looking at this three-dimensional mapping of volumes and try to come up with some criteria that tells us that our mapping is decent and that we can use now the nested solution or the nested mapping to force to run the nested model. Okay, so I'm going to stop here for this tutorial and we're going to start the next tutorial very soon.